Right, today we're going to learn a little bit about sex-linked traits, and in order to do that we're going to first review what a karyotype is. Now karyo means nucleus, so all of these chromosomes that we would find in a human we would find actually in the nucleus, and when the cells are undergoing mitosis, when they're condensed and we can actually see them, that's when researchers can extract the DNA and actually put all the chromosomes in order from their size, and here they would be in homologs. Actually, they would be tetrads because these are duplicated. So these are tetrads lined up, but one of these you got from your mom and one of them you got from your dad. So chromosomes 1 all the way down to 22, so all of these chromosomes. And actually, let's box those up. So all of these chromosomes here, 1 through 22, is actually, we consider those autosomes. Auto means everybody, self, soma means body. So literally translated, they're the chromosomes that kind of make us, or make our bodies, what they actually look like. So we call the chromosomes 1 through 22 autosomes. Now the other chromosomes, the X and the Y chromosome, my line color here always is bad, so we're going to do this here. So these chromosomes here are actually considered our sex chromosomes, X and Y. Now this would be a boy. If it was a girl, it would be XX. So when we talk about a sex-linked trait, that means that the gene that's on one of these chromosomes, and it could be either the X or the Y, has within it a gene that can infer like a disease, a condition, a syndrome, or something like that. And a classic example would be color blindness. Color blindness is actually located on the X chromosome, so it's a sex-linked recessive disease, and we actually find that, or not really disease, a syndrome or a situation or condition I should say, we find that on the X chromosome. We do not find that on the Y chromosome. So again, we're first going to go over the sex-linked disorders, and just keep in mind that those are inherited on these chromosomes. And that's an important thing to realize because we're going to be using these X's and Y's when we do our Punnett squares. So for sex-linked traits, for our class right now, we're just going to focus on the X chromosome. There are some Y-linked diseases and conditions and syndromes and whatnot, but we're going to focus in on the sex-linked that are on the X chromosome. So girls, we denote them genotypically with X and an X, and boys we denote an X and a Y. And how we would write those if we were doing a Punnett square, if the girl is totally normal and does not have, say, color blindness, this is what her genotype would look like. If she's a carrier, she would have one X and X prime on the other one, and that can go on the first X or it could go on the second X. I typically actually do it on the first X, to be honest with you. I don't really forgot why I did it here on this one. And if she actually has color blindness, she has to have two X chromosomes that have that particular gene for it. So there's 3 options for girls to have. Boys only have 2. They have an X and a Y, with this X not being affected at all, or they have this combination when they're affected. So the X chromosome here actually has that gene on it. Now remember what I said earlier, sex-linked, we're going to focus on sex-linked that are on the X chromosome, and actually the ones that we are going to focus on are recessive. So they actually don't do the talking when there's another chromosome around that is normal. Now here we only have one X, so even if it's recessive, it's doing all the talking because there's not another X there. So this means that this person is affected. This boy has an X chromosome that does not carry the gene, so that X is doing all the talking. So we have 2 situations here. If we go back to the girl, she has 2 normal X's. They're both communicating and talking fine, and there's no color blindness here. here's the gene for color blindness, but that's being overshadowed because it's a recessive disease by this other X that's doing all the talking. Here, 2 of these X chromosomes both have the gene, so there's not another dominant X chromosome that can actually do the talking. So here we actually see that the girl would have color blindness. Now, one thing to note here is that there's only an opportunity for girls to be a carrier. So a question could ask, what's the probability or what's the chance that a boy could be a carrier for a sex-linked trait? And in our situation, since we're dealing with X chromosomes, there's no opportunity for a boy to be carrier, so don't ever take that bait, as I say. Here they're normal or they're affected. They never are a carrier. So a lot of people sometimes look at this and say, oh, he must be a carrier, but he can't be because he doesn't have that other X that would actually do the talking that's normal. Only girls can be carriers of sex-linked recessive diseases. So let's actually go to our practicing. So here we have a woman that is a carrier crossed with a man that does not have color blindness. So we're going to take these alleles, put them on the top, take these alleles and put them down, and then just fill in our box like we normally would for a monohybrid cross. Once you actually have that done, I'd like you to answer these questions. How many girls would have the disease? Not be a carrier, but I'm actually asking how many would have the disease. How many boys would have the disease? And then how many children would have the disease? And in this situation we're using color blindness, so let's just stick with that. So why don't you pause the program right now, try to do the problem, and then come back when you're ready. Alright, this is what it should look like. Here's the woman at the top, she's the carrier. The man is normal, and we filled in the Punnett square just like this. So how many girls would have the disease would be 0. We have 2 girls here, and neither one of them show the disease. How many boys would? Here we go. Now remember, we've got 1, 2, 3, 4 children. So how many boys is not asking how many children, how many boys. So like, oh, okay, here's all the boys. So I only have 1 of the 2 boys, so that would be 50% of the boys would have the disease. The last question is how many of the children would have the disease. So I have 4 children here, right? Only 1 has the disease, so that would be 25%. Another question could be, what's the percentage of children that would be carriers? Well, we've got 1 children that's a carrier, no, and we're not going to take the bait that he's a carrier. So we only have 1 out of 4, so that would be 25%. Okay? Another question could be, out of all of the girls, what's the percentage of girls that would have color blindness? Again, that would be 0. What else could I ask? Out of all of the children, how many would be normal? And that would be 75%. So we have 1 that's normal, 1 that's normal here, and 1 that's normal here. So that's 3 out of 4. So normal meaning that they don't have the disease. Now again, if I'm asking those questions, those are phenotypic questions. That's not asking anything about their genotype. So genotype questions would have to ask how many is a carrier. So if I'm just asking if they have the disease or not, we're going to just look at whether they have it or not. So now it's your turn. So I've got 4 different crosses here, and I'd like you to calculate the crosses. So you're going to do for each one of these, and actually if you could list them as 1, 2, 3, and 4, that would be great. And then for each of them, separate the girls, how many the girls would have the disease, how many the boys would have the disease, and then how many children would have the disease. So these 3 answers should be provided with every single Punnett square. So make sure your work is neat, it's legible, I can understand it, and bring that to class, next class, and we can go over it. Good luck!